So as we started talking about matter a couple of weeks ago, we already said that the atom or elements are the smallest we can divide matter into, because once you try to divide an atom or the element, not longer is possible because you cannot break an element into smaller pieces. That's the smallest you can divide matter. So we are going to take a look at how the atom was discovered. There's a couple of experiments and scientists that are important and that we have to make sure that you understand, because we don't do it to talk about the atom if we don't talk about how it was discovered. So before we do that, let's see here. Yeah, we're jumping right into it. So we are going to start with this Greek scientist way back when there was no lab equipment, where there was no way to see anything, or at least how things behave. So this Greek scientist called Democritus started thinking and took a piece of bread and said, if I start breaking a piece of bread into pieces and I keep cutting the bread, there's going to be a time where I cannot cut that bread anymore. So things behave the same way. So matter should be behaving the same way. So I said, okay, that smallest particle that I cannot divide any longer, I'm going to call atomos. And atomos means uncuttable, means it cannot be broken apart any longer. And that's the first time that somebody spoke about the atom. Now, he was a Greek scientist, so he went to the council of Greek people and said, I have this particle called the atom. You cannot see it, but it's there. And everybody laughed at him because they couldn't see it, they couldn't believe him. But somebody there, which happens to be Democritus apostle, one of his students, he said, he might be right, but let's rephrase all this. And he presented the idea again, and they believe Aristotle, which was a student, and not Democritus. But we still give credit to Democritus, and we said, yeah, he was the one that discovered it, not Aristotle. So the first time, Democritus, atoms are undivisible, uncuttable, so they cannot be broken apart. Then before we start talking about the others, let's go over a couple of laws here. The law of conservation of mass, which matter is neither created or destroyed, meaning that the mass you start with, you have to end up with. So if I start with 100 grams of reactants, I need to end with 100 grams of reactant. It's not easy as it's making it sound. When we get to the mole and stoichiometry, we'll deal on how to deal with the conservation of mass to make sure we comply with it. We also need to talk about chemical reactions in order to do that, but we'll start with that after example. Then we have the law of constant composition, which says that a compound always contains elements in the same ratio. Meaning if I have a compound made of carbon and oxygen, and I find another substance that is made of carbon and oxygen, as long as both have the same ratio of carbon and oxygen, they're both the same material. So ratio of elements in a compound is crucial. As long as the ratio is the same, we have the same substance. Argue they're different, they have to have the same ratio. If the ratio differs by a little bit, it's no longer the same substance. It has to be exactly the same. And then we have the law of multiple proportion, and that one just says that we can have compounds made of the same element, but if they combine in different ratios, then we have different substances or different compounds. So we can have SO2 versus SO3. They're both made of sulfur and oxygen, but one has one more oxygen, making it different. So we have these three laws, and they're important because they help us understand our next scientist, which is Dalton. Dalton came out with the Dalton atomic theory. It's a theory that we are still using today. It's a good theory. There's a tiny, tiny, tiny mistake in the theory. Well, it's not a mistake, it's a revision. I'll tell you about it in a little bit. But what Dalton says in his ideas is that elements are made of particles called atoms. And all atoms of the same element are identical. So if I can have two particles of the same element, two atoms, they're all the same substance. So all atoms are made of the same identical type of atoms. And then I can combine atoms to make compounds. So first postulate, elements are made of atoms. All atoms of the same part of the same substance are the same. Second one, I can combine elements to make atoms. To make compounds. Let me fix that. And I did it again. Then he said that the ratio of elements to the same compound remains the same. If you change that ratio, you change the compound, which is that law of composition that we mentioned before. The last one is matters cannot be created or destroyed, which is the law of conservation of mass. And that's why he made his mistake. And it's not that it's a mistake, it's just that based on the information he had at the time, he couldn't predict things that are happening today because he didn't have the instrumentation to do it. So what the problem was is that now we know that we can create atoms, we can destroy atoms, because we have these things called nuclear reactions. And nuclear reactions allow for atoms to be created and destroyed, something he wasn't aware of, and he wouldn't be because he wouldn't have the instrumentation to do this. You have to remember, depending on the time, there's only so much instrumentation they have. And even if you have a law, that law can be revised based on new discoveries. And that's how we can modify that Dalton atomic theory, knowing that the law of conservation of the mass is not always conserved. Okay, so after Dalton, we jump a little bit time forward, and we run into this scientist called J.J. Thomson. He discovered the electron using this instrument called the cathode ray tube. You guys are too young for this, but if you, I don't know if you went to your grandparents or grandparents' homes and you saw those big TVs with a huge tube inside. That tube inside the TV, that's a cathode ray tube. What it does is it has two electrodes. You have a cathode and an anode, and once you put voltage to it, it generates a current that goes from the cathode to the anode. The cathode is a negative charge, and it gets attracted towards the anode, and the anode is positive electrode, and because it's getting attracted from the negative to the positive, we know that those rays are negative. They have to, because different charges attract, same charges repel each other. So that electrical charge is negative in nature. It's attracted to the positive electrode, and we can manipulate that by adding a magnet to it, and we can make it move towards a positive magnet. We're not going too much in details on how that works. Just know that it's something that can be done. Because those particles going towards the anode are negative in nature, that's why he called them electrons. So Dalton was the theory of the atom, and now we have Thomson, and Thomson is all about the electron using the cathode ray tube. Now he came out also with this plum pudding model. And the plum pudding model, all it says is if I have a sphere that's positive in nature, I can have these small areas with negative charges. And if you look at a plum cake, it's bread with plums, chunks inside. Those chunks of plums are the negative charges. There's a huge problem with the cathode ray tube, which I'll mention a little bit later. But still good that the electron was discovered. Then as we move forward, we now have a German. Okay, so this is just a plum pudding that I just mentioned, so not going over that again. We have this German called Rutherford. And Rutherford was all about the gold foil experiment. The gold foil experiment uses a particle source that's positive in nature. So let me add that in there. So it generates positive alpha particles that are used to bombard a piece of gold foil. Then we have a detector around the gold foil to see what happens to those particles as they hit the gold foil. He thought, okay, if I hit a piece of gold foil, I will expect all those particles that are positive in nature to go through. But that's not quite what happened. He was expecting for that those particles and they to go through because they can go through the gold foil. But he saw three things, and you need to know these three things. The first one is the particles went through. Nothing happened. So they went through the gold foil. So and they went through because the atom is almost empty space. So the atom is mostly empty. There's nothing there because they're so small, those particles were able to go through. Now, sometimes those particles got bounced back or they rebound. And they bounce back because he was able to say that the atoms must have a dense center. So all the mass of the atom is concentrated in one location. He called that center the nucleus. So now we have particles going through, we have particles bouncing back. So atom is empty space with its dense center, with a nucleus. That sounds like what we know today. That's good. So the third thing was that sometimes the particles got deflected. So if I have a positive particle going towards the center of the atom, and I'm able to move that particle a little bit, what does that say about my center in the atom? What charge should it have? Positive, because if positive and positive repel each other. If the nucleus was negative, it would have gotten attracted. That will be a big problem. So it goes deflected. So now, when the particles are deflected, it's because the nucleus is positive. So there are particles inside that nucleus that are positive in nature. He called those protons. So summarizing this, we have an atom that's almost empty space. It has a dense nucleus, and that nucleus is positive in nature. So the atom has protons in the nucleus. So JJ was about the electron, Rutherford was about the protons. The cathode ray has some problems. The gold foil experiment has other problems. But let me see what is coming up here. Okay, so after these two experiments, we can come up with what is called the nuclear model, which says that the atom is almost empty space with a center that has all the mass of the atom and is positive in nature. And those electrons that JJ discovered are outside somewhere around that nucleus. So first problem, JJ said that the atom behaves like a plum pudding, which is a sphere that's positive with embedded negative charges. That's not what we see, but we cannot explain why yet. Then we have Rutherford that says that the center is positive, but the particles that are negative are outside the atom. Well, if we have positive particles and we have negative particles, they should be attracting each other. And that's not what happens. But we cannot explain that yet. We're going to have to wait to be able to explain why those two experiments are wrong until we get to electronic configurations and we talk about the electron more. And that doesn't happen until like 4 weeks from now. So you're going to have to wait on that. So from the experiments, you just know Dalton with the postulates, you know JJ, the experiment, and what he discovered, Rutherford, the gold foil, and what he discovered with that, and you should be okay for the exam. Alrighty. So if we summarize what we've done so far, we have an atom that has protons, neutrons, and electrons. Wait a second, where those neutrons come from? We only discovered the electron and the protons from what we've done. Well, there's another scientist that we don't speak a lot that discovered the neutron, so it's called Chadwick. And that's all you're going to get in terms of the neutron. Chadwick discovered the neutron. He did an experiment that's similar to the gold foil and found that those neutrons have no charge. We have protons that are positive. We have electrons that are negative. The mass of the protons, we are going to say they're around 1 AMU to just say that they have mass. Neutrons have similar masses. Neutrons are there to stabilize the atom. Electrons, we say that the mass is around 0. They really don't have a mass. But they account for all the properties of the atom. Crazy. Protons and neutrons are located in the nucleus, and then we have the electrons located outside the nucleus. So later on, we're going to have to deal with the issue of why the particles don't get attracted, so why those protons are not attracting electrons, and what is keeping the electrons outside the nucleus. We'll deal with that later on. So those neutrons have a mass similar to the proton. They're there to kind of stabilize the atom. If you did your atom lab that you had assigned to you, you should have seen that sometimes you can change the number of neutrons and nothing happens to the atom, but sometimes you can change the number of neutrons and will make that atom unstable. We'll deal with it cases where the neutron can be changed and still stable. We'll deal with what happens to the electrons and we change that. Protons, they're kind of important and we cannot touch them too much. Protons are the ones that identify the element. Protons is the same as the atomic number. So if you have the symbol, you'll see that from symbol to symbol, if you have carbon, next to it is nitrogen. As we change the atomic number, carbon is 6. By adding 1 proton, we get 7 protons, atomic number 7. If we change the atomic number, we are changing the identity of the element. We are changing how many protons that element has. So we do never touch protons unless we want to change the atom. Again, atomic number, which we use the letter Z to represent that, is how many protons you have in the nucleus of that atom, which means how many positive particles you have in that nucleus. Then I told you that we can have an atom that's stable with different number of neutrons because the number of neutrons is changing. So we can have something like carbon 12, carbon 13, carbon 14. They are all carbon atoms, so they all have the same number of protons, 6 protons. But then I can have carbon 12, which has 6 neutrons, carbon 13, which has 7, and carbon 14, that have 8. So we need to explain that a little bit. So we are going to say that atoms with the same number of protons with different number of neutrons, we are going to call isotopes, which creates a small problem that we are going to solve towards the end of today. And because the mass of the atom comes from the nucleus, and in the nucleus we have protons and neutrons, we are going to calculate this new thing called mass number, which is the sum of the protons and neutrons in the nucleus. So isotopes are atoms of the same element with different weight. And I want you to be careful with this because we also have this thing called atomic mass. And atomic mass is not the same as mass number. Atomic mass is the rounded, mass number is the rounded atomic mass. So we can say this. And there's a reason why it's rounded, and that is because we cannot have a fraction of a particle. And the atomic mass implies that we have a fraction. And we cannot have half a proton or half a neutron. We either have a proton, we either have a neutron, or we don't have them. We'll deal how to reconcile the atomic mass and the mass number in a little bit. Okay, so let me see what's coming here. Okay, let's do this before we move on too far. Let's say I have aluminum. Aluminum is Al, which is its symbol. From that, and looking at a periodic table, we should be able to tell what the atomic number is. What's that? AU is called. We're doing with aluminum, Al. So aluminum, which element number 13, means that we have 13 protons because the atomic number is the same as the number of protons. Because atoms are neutral, meaning they don't have a charge, the number of electrons should also be 13. So when you add the positive charges and the negative charges, the overall charge will be 0. You don't want a charge for the atom. So you are going to assume the atom is neutral unless I give you information telling you otherwise. So atoms are neutral. Okay. We can take the information that we have so far and write that in a way that we can tell what we have. So we can use a symbol, Al. We can use that Z, and then that other number called A. Z is the atomic number. So we can say, we can have aluminum 13. A is the mass number. And I told you the mass number is the rounded atomic mass. So for aluminum, the atomic mass is 26.982. So my mass number should be 27. So I'm just going to put it 27. So if I have 27 as my mass number and I have 13 protons, how many neutrons I have? The number of neutrons is the mass number minus protons. So if I had 27 for my mass number and 13 protons, my number of neutrons should be 14. Okay, because 14 plus 13, that's 27. And if you write it the way I did with a symbol AL with a 27 on top and the 13 at the bottom, if you take the 27 minus 13, that gives you neutrons. 13 gives you the protons and electrons if the atom is neutral. Now, I could also have aluminum 2813 or aluminum 2913. That means that those two at the bottom, those are isotopes because the mass is changing, which also tells you that the number of neutrons is changing. So instead of having 14 neutrons, you have 15 or 16 neutrons. And that's okay to have. Changing the number of neutrons is okay to a certain degree until it keeps the atom stable. If the atom starts becoming unstable, then you cannot change those neutrons. Okay, so let's move on to this other case now. When we change the number of electrons, if we change the number of electrons, the atom is no longer neutral. It is going to have a charge. The charge will be determined by how many electrons you have. And you can either have an atom that's positive, and we are going to call a cation, or we can have a negative atom, and we're going to call it an anion. You can calculate the charge by taking the protons minus electrons. So if that difference is positive, then the atom will be a cation. If that difference is negative, it means that it's a negative atom. We always talk about charges in terms of electrons because those are the particles you can change. We never say, I take protons out to make it positive or negative because taking protons out implies changing the identity. So only deal with electrons when dealing with charges. And when we have a positive charge like Ca plus 2, we write it on the top right, and that's how you know that atom has a charge. If it is negative, like and then nitrogen minus 3, then we do it on the top right as well. So let me see what's coming here. Okay. So let's say I have calcium plus 2. Let's see if we can calculate the protons, electrons, and neutrons. Give it a try. Take a minute or two and try to figure it out. How many protons, electrons, and neutrons does calcium have? If you don't have your reference table and your periodic table, calcium is atomic number 20. Okay, so having calcium being atomic number 20 tells you that you have how many protons? 20, right? If the atom was neutral, you will have 20 electrons. But because you have a +2, that means you have how many less? 2 less. So instead of having 20, it will be 18. And then the neutrons, you need the mass number. So for calcium, it is 40. Okay, that's ugly. So it is 40 minus 20. That's 20. Nice. Let's do one more. Let's say I have oxygen, and that's 8 16. So protons will be 8, but electrons will be, okay, I need a charge in there for this to work. So instead of 8, it will be 10. And then neutrons is 16 minus 8, which is 8. Yes.
For the first one, oh wait, sorry, I read that wrong. Because the nouns and the protons, they add up to make the mass, right?
Protons and neutrons add up to make the mass, yes. It's neutrons plus protons. So it is 20 plus 20, which is 40. Now, these two examples, the number of neutrons was nice to calculate, and it turned out to be the same as the number of protons. That doesn't always happen. So it's based on which element you have, so you have to be careful. Don't be fooled. Okay, so now I have isotopes, which could have different masses. I have ions, which could have different charges. And still, we haven't answered why the atomic mass doesn't equal the mass number. Mass number implies the mass of one atom. Atomic mass implies the mass of all the atoms of that particular element. So we need a way now how to reconcile one from the other. So how do I go from the mass of one to the mass of all? So I can go on a scavenger hunt and go find, let's say, carbon in nature. As you do that, you are going to find different versions of carbon with different masses. But as you're doing that, some of those isotopes or versions of carbon that you find in nature are going to be more prominent than others, meaning you're going to find some type of carbon more than other types of carbon. So the percent abundance of one of those isotopes of carbon is going to be higher than the other isotopes of carbon. And the isotopes are the different versions of the same element. So I have all this information now. I have masses of different isotopes. I have how much I have of those different atoms or isotopes. So we are going to do this thing called weighted average mass, which is going to equal the atomic mass. And the weighted average is going to take into consideration how much of that atom is found in nature and the mass of that isotope that's found in nature. So the atomic mass we are going to define as the sum of the isotopic mass of one type of atom times how much of that atom is found in nature. The how much is a fractional abundance, it's a percent that we're going to use it in decimal form. And when we do that, we just add all those multiplications. And when we add up those multiplications, the result at the end has to equal the atomic mass that's in the periodic table. So this sum is just saying, okay, for isotope number 1 is the mass of that isotope times the percent abundance, plus the mass of the second times the percent abundance of the second, and so on. So if we take this example of, this is this silicon has a, for silicon 29 you have a 4.67% abundance. For silicon 30 you have 3.113. For silicon 28 you have 92.2%. What this is telling you is that silicon 28, because the percent abundance is the highest, contributes the most to the mass of silicon. And when I look at the mass of silicon, it is 28.086. So it's very close to the silicon 28. The rest of the mass is coming from the contribution of the other two isotopes, well, because their percent abundance is so low, they don't contribute a lot, so they don't change the mass of silicon a lot. Now, to convert those percentages to a decimal form, which is the easiest way of doing it, all you have to do is take that percent and divide by 100. If you do it as a percent and multiply the mass times the percent, then at the end you have to divide by 100. It is just easier to convert the percent into a decimal because it gives you the best result. And do not round numbers. You guys are good at rounding and forget about sig figs. Don't do that. I'm telling you, do not round. These atomic masses, at least for the periodic table I gave you, are done to 3 decimal places. So your calculation should have at least 3 decimal places as well, because you're adding and multiplying. And if I just make a generalization, 3 decimal places for atomic masses, you'll be good. Okay, so the mother atom is identified by the number of protons it has. The number of neutrons are going to help you identify the type of atom you have for that same element. And then the number of electrons are going to help you with what charge of that element should be. And then we had the atomic mass, which was calculated from the masses of all the atoms for that particular element. Okay. With this, we finish chapter 2. We have a small portion on the periodic table, which we'll do really quick. Next, we still have plenty of time. Again, by doing the lab, the atomic mass, the atomic lab that I gave you on the polio, on the atom, you should be good because it covers all of this. Again, so what I just did is just summarizing those two activities. You still have a homework, you still have a quiz on the atom. I think they're due this weekend. Please don't forget to do those. Okay, so let me finish with this and change gears.